Well, this video is going to be about fixing air conditioners, but first I've got to give you a lesson on heat so that you can understand how air conditioners work and probably a lot of other things. First of all, there's no such thing about, it's called creating cold. Cold is just an effect of removing heat. That just means there's less heat. Even when it seems really cold outside, it's still way above absolute zero, so there's still a lot of heat. All the heat that was in the universe originally when the Big Bang happened, you know, like 14.5 billion years ago, and all matter and all space was created, is really still here. The heat in the universe is either just floating around as moving particles about the size of electrons or photons, or it's encapsulated around the neutrons and protons in every atom. In every atom, the tiniest part in the middle is neutrons and protons, and then there's this massive space, like the size of our solar system, like in a ratio of the sun in the middle to the distance of our whole solar system with all the planets, of empty space, which really isn't empty. It's all encapsulated little heat particles trying to get out. So if you split one atom, there would be enough heat in there to vaporize your body. When a nuclear bomb goes off and a series of atoms are split in an exponential pattern, then what is happening is the heat that is encased around the electrons orbiting the atom, or at least the particles in the middle, is released. And that is like probably about 98% heat and about 2% other energies like light and gamma radiation and radiation from all other wavelengths of the electromagnetic spectrum. Heat has mass also. That means it can be sucked in by a black hole and never escape, or it can be bent by passing by a large object with a strong gravitational force. It also has kinetic energy. That's how heat actually heats things up. The kinetic energy of heat works by the fact that these little particles are hitting things. They're hitting the molecules and the little parts that make up everything that we know and see and touch. It's causing those parts to vibrate, and the vibration is an increased amplitude of the natural motion of that molecule or atom, and that is described as heat. Looking down long roads, laneways, deserts, whatever, with a lot of sun and heat, from a distance you get something like a mirage, like a reflection of wiggly air, or may look like water. Well, this is an interference effect. The light photons are coming down, of course, the speed of light, and the heat is also coming down at the same speed. When those short waves hit the ground, they change to long waves, and then they are re-radiated back, and when that happens, they're interfering. The particles are colliding, heat particles and light particles, making that image. Now, heat comes in more than one wavelength. There's long wave, short wave heat, infrared, except a little bit of band space in the electromagnetic spectrum. For example, when it comes down from the sky and passes through your windows of your car or whatever, it's traveling as short waves. Short waves are good waves that like to penetrate things, that penetrates the atmosphere well, penetrates clouds well, stuff like that. Well, the problem is, when heat passes through glass, through moisture, through carbon dioxide, or some other mediums, it gets changed to long wave radiation. And long wave radiation does not like to escape very easily through surfaces like this, like glass or, the clouds. That's why on a cloudy evening it actually stays warmer. The clouds insulate the earth because the long waves are bouncing off the water particles and coming back to earth, and you're feeling them. Greenhouse gases like carbon dioxide and methane and stuff like that make a very good reflector for heat, and that warms our atmosphere a little bit more too. The density of our atmosphere actually is what retains most of our heat and what makes us feel warm. See, if you go up Mount Everest or very high in the sky like an airplane, it's very cold up there, yet it's very warm on the earth. The reason is the air is a lot less dense. On planets with no atmosphere, they are scorching hot in the daytime, but in the shade very cold, and at night extremely cold. Heat gives everything much of its properties. you know, kind of its texture a little bit, how soft or hard it is. If there was no heat and everything was at absolute zero, everything would be infinitely conductive, like a superconductor, and have weird properties, and all gases would be solids. I find heat and gravity to be my most fascinating topics of science to think about and to want to understand. Here's an experiment for anybody to try to show you some of the properties of heat you're not normally aware of. Take any ordinary syringe, the plunger is fully depressed like this, melt the end together or somehow cork the end with whatever you want to cork it with, then pull out the plunger on the syringe to almost the end and create a vacuum in there. If you let go, it releases very quickly and comes slamming to the end, and of course there's no space again. But do the same thing over again, and this time when it's all the way pulled out, put a vice grip on the plunger shaft, and that keeps it held out against the pressure of the air. Now that it's still corked, there's a lot of empty space in there, a vacuum. Well, it's not really a vacuum for long. Something goes in there and starts to fill up some of the space, and it isn't air. Sure, something did happen while you were doing that. Because you made a vacuum, there was less heat in there. That made that space in there cooler. But eventually that space warms up again to the same temperature as in the area that, of course, the syringe is in. After several minutes, if you release the vice grip, the plunger, of course, will suck itself back, but it will stop about there. And if you try to push it and squeeze it, you know, push it down, it'll bounce back out. So you think somehow air got in there. Well, air didn't get in there. Heat got in there. And since I said heat has kinetic energy, which is the energy of motion, so if it hits something, it causes it to move or to vibrate. Well, since heat got in that syringe while it sat there, now it's pushing on the plunger, just like air pressure. It's little movement of particles zigging around in there are hitting everything on the inside walls, just as if there was air in there. So when you try to push the plunger back in, it tries to push the plunger back out a little bit, yet there's actually nothing in there. It's, well, except heat particles. It's a vacuum. Then if you just leave the syringe sit there all by itself, air pressure will eventually take over, and will slowly push the plunger back to the original spot where there was no space. And the heat will be pushed back out again. Cool. Now you can start to understand how an air conditioner works. The front section of the air conditioner radiator and all those tubes is called the evaporator. That's where the lowest pressure is in the air conditioner. The back side's called a condenser. That's where the highest pressure is. Now since there's a gas in there under a lower pressure than it would like to be, it's lacking in heat. Well, just like the syringe, when you suck air across all those little fins, transfer to the tubes, and that allows heat to penetrate inside and fill up that less pressure space and warm up the Freon. But of course, when the heat goes in there, it's actually taken away from the air, so the air now has less heat in it and less moisture, and the gas inside now has more heat in it. So the heat now is traveling in the warmed up Freon and then goes to the back of the air and is blown out as exhausted heat. All air conditioners have a compressor. This one's called a rotary compressor. Some have an oval compressor. This is called a piston compressor. It actually looks like a little lawnmower engine in there with a piston and valves and an electric motor driving it. Inside this one, it looks more like a hydraulic pump with a round thing with fins on it rotating in an off-center space. All compressors have an input and output. That's called a suction line. That's input. It's called an output line, the high side line or pressure line. They all have two radiators, not always in the same box, just like in central air conditioning. The one radiator can be outside of the house and the other one inside of the house, in the furnace. And they all have a fan motor. One to suck air in the front and blow it out, and the other one to blow air out the back. So I made a diagram to show you how the system works. This is how all compressor-based air conditioning systems function. First you have a compressor. Of course it sucks gas in, Freon,
squishes it to a much smaller space. When it does that, there's not enough space in there anymore to easily hold the heat that was contained in that gas. So the heated gas now goes through the coil called the condenser. This is like a radiator. The tubes just loop back and forth. Then they come out. A fan blows in that radiator to dissipate the heat and cool it off to room temperature. When the hot gas exits, it's now turned into a liquid because it's been cooled. Goes to this little tiny tube, skinny tube. They're actually a few feet long. The tube looks just like a wire, but it's actually hollow. The reason you do have this long, skinny, restricting tube that forces the Freon through very difficultly is so that it can create back pressure, so we maintain liquid Freon on the condensing coil. By the time the Freon goes the distance of that tube and gets to the evaporator, it is all the largest diameter tubes on the air conditioner, much larger than this tube. This gives the liquid Freon someplace to want to expand, and when a liquid turns to a gas, that's called evaporating, and it makes itself colder. So the liquid Freon is now foaming and bubbling as it's going through all these little tubes, and the fan is blowing on the radiator. By the time it gets to the top, or the end of the radiator, it's now a pure gas. Well, the pure gas is now warmed up to whatever temperature the room is where the fan is. Then the pure gas goes back to here, now containing quite a bit more heat than it did before, especially than when it came out here, and gets recompressed again. And then the heat, of course, is exhausted by the condenser. So that's how all systems work. This cap line isn't always used. Sometimes they use something called a TX valve or a thermal expansion valve to create back pressure and reduce the flow of Freon. A refrigerator works exactly the same way, just at different pressures and with a different gas. A freezer works the same way too, and so does the air conditioning in your car. Exactly. Freon in the air conditioner while it's running and these tubes in the evaporator is at about 66-67 psi if it's working correctly. In the hotter back condensing radiator, the Freon exists at about 170-180 psi. When there isn't enough Freon in the system, it's low, all the tubes will not get cold like they're supposed to, only some of them will get cold, and they'll also form ice on the tubes, and that's bad, and that needs repair. In my next video, I'll describe how to repair air conditioners now that you guys have a bit of a redneck understanding how to understand heat and how, at least see how an air conditioner works.